It is my pleasure to introduce Dr. Kelly Goldsmith, MD, as our speaker for today. Dr. Goldsmith is professor of pediatrics at Emory University School of Medicine and holds a Curing Kids Cancer Chair in Pediatric Oncology. She is clinical director of the neuroblastoma program and the Aflac Precision Medicine program at the Aflac Center and Blood Disorder Center at Children's Healthcare of Atlanta and co-leader of the Discovery and Developmental Therapeutics Research Program at the Winship Cancer Institute. A translational physician scientist, Dr. Goldsmith focuses on new therapies for children with neuroblastoma. She co-led the first in-children trial of lorlatinib for ALK-mutated relapse or refractory neuroblastoma, supporting its incorporation into a phase 3 trial for newly diagnosed high-risk ALK-driven disease. Her NIH-funded laboratory studies demonstrating the anti-tumor activity of ex vivo expanded gamma delta T cells with dinutuximab led to an ongoing first-in-human phase 1 trial of allogeneic gamma delta T cell therapy for children with relapse or refractory neuroblastoma and osteosarcoma. She has also co-led multiple national clinical trials through the Children's Oncology Group and the NAT Consortium to expand access to innovative therapies for children with high-risk disease. Dr. Goldsmith was awarded an ALSF REACH grant in 2021, has previously served as an ALSF post-program mentor, and is currently an active reviewer for ALSF. So on behalf of ALSF, I wanted to thank Dr. Goldsmith for her time today, and we'll pass over to her for a presentation titled From First Responders to Cell Therapies, Harnessing Innate Immunity for Pediatric Solid Tumors. And as a quick programming note, we have a Q&A session after the presentation, and you may ask questions to Dr. Goldsmith using the chat feature. So with that, I will pass it over to Dr. Goldsmith, and thank you again for your time today.
Great. Thank you so much, Justin, for that nice introduction. Thanks so much for the opportunity to speak today at the ALSF seminar series. I actually trained at CHOP and remember Alex and her bright smile on clinic days that I shared with her primary oncologist, so this is really an honor. Today, I'm going to talk about how innate immune cells, who in their day jobs are known to be first responders to cell stress states like infection, and talk about how we can harness those properties to really develop a novel and potent cellular therapy against pediatric solid tumors. So today I'm going to give an overview of neuroblastoma. We'll talk about how we can enhance GD2 chemoimmunotherapy with innate immune driving agents, and then talk about gamma delta T cells and how they could be used as a novel adoptive cell therapy approach in combination with chemoimmunotherapy or alone. We want to talk about going beyond GD2, and we'll discuss why, to engineer potent second generation gamma delta T cells, and then we'll finish up with talking about how to better model the tumor microenvironment to translate these therapies to our patients. So most people on this call likely know what neuroblastoma is, but for those of you who may not, it is the most common extracranial solid tumor of childhood and is derived from the embryonic solid tumor cells in the peripheral nervous system. And while it makes up only 8% of pediatric tumors, it's responsible for about 15% of childhood cancer-related deaths. And that's because the majority of patients present with a very aggressive form of this tumor we call high-risk disease. The most striking aspect of neuroblastoma, especially from a research perspective, is its clinical and biologic heterogeneity. It often can present as a single isolated lesion that spontaneously regresses. It can also present in patients under 12 months with metastatic disease that goes away on its own without chemotherapy. But as I mentioned, a very large portion of these patients present over 18 months of age with widely metastatic disease or with tumor harboring the proto-oncogene MYC in its amplified state. And as such, it's these high-risk neuroblastoma patients that we need to find better therapies for. So neuroblastoma actually is one of the few pediatric solid tumors that's proven sensitive to immunotherapy approaches. And that's because the majority of neuroblastoma tumors express the cell surface diacylganglioside GD2. So dinutuximab is just one of many anti-GD2 antibodies. It's a chimeric humanized monoclonal antibody that targets GD2. And like many antibodies, it requires antibody-dependent cellular cytotoxicity to work. And I wanted to mention this because in talking about the innate immune system and harnessing that for therapies, it's those subsets of the immune system that are necessary to recognize the antibody-coded tumor. And that's because innate immune cells like NK cells, gamma delta T cells, monocytes, neutrophils, and others express this receptor on their surface called the Fc gamma receptor 3 or CD16 that recognizes the antibody coding the tumor-specific antigen. As such, when we give antibodies like dinutuximab, we give it with myeloid growth factor that can augment and increase the numbers of these cells in the patient. And so, incorporation of dinutuximab and myeloid growth factor into the maintenance phase of patients with newly diagnosed high-risk neuroblastoma significantly improved patient event-free survival by up to 20%. And this ultimately led to FDA approval of dinutuximab in March of 2015. And this is just a survival curve showing that difference in survival. In a subsequent phase 2 trial through the Children's Oncology Group, high-risk patients who were refractory to induction therapy or who were in first relapse were randomized to receive irinotecan and temozolomide chemotherapy combination with either the mTOR inhibitor temsirolimus or dinutuximab. And what we didn't expect was that the dinutuximab arm had a pretty impressive response rate of CR and PR of 53%. And what was even more remarkable was that patients who had been pre-treated with dinutuximab in the upfront phase of therapy, who were otherwise refractory to therapy altogether, and who had bulky metastatic disease, which isn't responsive to dinutuximab monotherapy, responded to this regimen. And so this really led to moving this cassette of chemoimmunotherapy upfront to treat patients with newly diagnosed high-risk neuroblastoma in pilot phases of other anti-GD2 antibodies, and ultimately in the currently enrolling Children's Oncology Group trial ANBL 2131, which is a randomized phase 3 trial looking at adding dinutuximab to induction chemotherapy for newly diagnosed high-risk neuroblastoma patients. But all of this really established a pipeline of trial concepts investigating additional agents to augment GD2 chemoimmunotherapy. So could we improve upon this really exciting antibody and chemotherapy cassette? So there's many ways to do it, but I think the overall premise is that we use agents that can enhance the innate immune response to the therapy that we're giving, the immunotherapy, dinutuximab, or other anti-GD2 therapies. So one such way is to use the polyamine inhibitor DFMO. So what is DFMO or eflornithine? It inhibits ODC1, which is the rate-limiting enzyme for polyamine synthesis, and it happens to be a downstream target of MYC-in, so it's going to be upregulated in MYC-in amplified patients. In addition, patients with ODC1 amplification in the setting of normal MYC-in copy number also have a poor prognosis. So what people don't know about DFMO is that it can also act as an immune modulator. So arginine, which is the precursor to polyamine synthesis, is known to be immunosuppressive in the tumor microenvironment. And DFMO could augment that by inhibiting polyamine synthesis to otherwise augment immune activity and infiltration of the immune system into the tumor. And this was shown preclinically here's one example on the right showing by Dr. Michael Hogarty and Hamid Paziri at the Children's Hospital of Philadelphia, where they showed that the TH-MYC-in transgenic mouse, when it was fed DFMO, had an increase in NK and dendritic cells, as well as an increase in cytokines needed to improve host immune response to immunotherapy. And so this led Dr. Meg Macy at Denver Children's and myself, or excuse me, Colorado Children's and myself, to propose a phase 2 trial of randomized study of irinotecan, temozolomide, and dinutuximab with or without DFMO in children with relapsed refractory or progressive neuroblastoma. And so my goals today are really to talk about the innate immune system effects and not to really go into the huge details of each trial because we want to get into the preclinical studies as well. So I'm really just going to talk about the overall trial results and how that kind of may or may not correlate with the immunophenotyping results. So overall, unfortunately, we found that the response rates to chemoimmunotherapy with DFMO were no different than chemoimmunotherapy alone. And as you see here, Arm A, which had no DFMO, had an overall response rate which is complete, partial, or minor responses per our INRC version 2.0 criteria in the neuroblastoma world. Had a 63% response rate, whereas Arm B that contained high-dose DFMO, which is 6,750 milligrams per meter squared per day, did not have any difference in response to at about 57.4%. The canonical response rates, as many of us think of as just CR and PR, also did not have a statistically significant difference in response. And as one might expect, we also saw no difference in the peripheral immune responses by DFMO, even with a 1 week lead in to truly deplete polyamines. As you can see here on the right in the pink bars on cycle 1, day 1, this actually represents 1 week lead in of DFMO monotherapy compared to a baseline in arm A that had no therapy yet at all. And this was all prior to giving chemo immunotherapy. And as you can see, there's really no difference in our cytotoxic neutrophils or any of our other immune cells in the peripheral blood of our patients treated on this trial. And so the question is it because DFMO is not doing clinically what we saw it do preclinically, or is it because we didn't really deplete the polyamines as we expected to in our patients? And unfortunately, I can't answer that right now, but I can say that work is ongoing in my lab and others to evaluate our patient samples on this trial for the polyamine depletion effects of high-dose DFMO within ANBL 1821. So hopefully those results will be soon to come. So are there other ways that we can augment a GD2 immunotherapy response? And how can we do that with things like external beam radiation? So as you may know, radiation changes the local tumor immunophenotype and can generate a systemic inflammatory response, although it's just locally radiating one spot. And that's because the immune mediators such as cytokines and immune cells are activated at the tumor site that's radiated and gets into the vasculature, into the bloodstream, and goes and causes an anti-tumor response in the areas that weren't radiated. This is otherwise known as the abscopal effect. Well, in neuroblastoma specifically, we have a systemic targeted radiotherapy that's delivered intravenously called MIBG when tagged to the radiolabeled iodine 131. And so we posited that maybe MIBG would enhance GD2 immunotherapy response through these same systemic inflammatory processes. In the meantime, we also had some data coming out through the NANT that showed that when the MIBG therapy is given with the histone deacetylase inhibitor vorinostat, that we had a superior response rates in relapsed and refractory neuroblastoma patients to MIBG monotherapy alone or to MIBG when given with this radiation sensitizer irinotecan. And what recently came out was that vorinostat not only could possibly increase MIBG responses, but is found preclinically to upregulate GD2, as you see in this far right panel, and it actually can have an anti-tumor effect by doing such by giving it in combination with an anti-GD2 antibody. And it may do this because it's been shown in other tumors to also inhibit the immune suppressive TME by inhibiting TAMs and increasing infiltration of anti-tumor immune cells. So this led to Dr. Thomas Cash, who's here at the Children's Healthcare of Atlanta with me, to propose the phase 1 study NANT 2017-01, which is a phase 1 study of I-131 MIBG with dinutuximab. That was the dose escalating portion of the trial in Part A. And Part B was to add vorinostat on for all the reasons I just mentioned in that combination for patients with relapsed and refractory neuroblastoma. And so I'm just going to focus on Part B of the trial here, that the overall response rates are really encouraging, that the CR/PR rate was 42% in this highly aggressively pretreated population who had all seen dinutuximab before. And the overall response rate with CR/PR/MR by our INRC criteria was 75%, with no patients having progressive disease on Part B of the study. And so what we found was also very interesting in the peripheral immunophenotyping of our patients on this trial was that the cytotoxic T cells in patients treated with vorinostat were lower in the peripheral blood compared to in the peripheral blood of patients treated with just chemoimmunotherapy alone at the end of one cycle. In addition, the early precursor NK cells, such as the CD56 bright, had increased in the peripheral blood of our vorinostat treated patients. And it's actually been shown that vorinostat may drive T cells into the tumor. And so we wonder if that's what's going on here in the peripheral blood as T cells are actually going into the tumor to have an anti-tumor response and coming out of the blood. However, of course, we need tumor tissue to confirm this hypothesis. and also to confirm that this vorinostat may select for early cytotoxic NK cells that go on to become your CD56 dim, CD16 bright cells that are necessary for ADCC. While we didn't see differences in the immunophenotype of responders versus non-responders, this was really a small number of patients, and I'm happy to say there's a phase 2 through NANT that is soon to activate, and we hope to do similar studies to answer these questions that are really provocative and may give us some biomarkers to look at. So, given dinutuximab and other anti-GD2 antibodies require ADCC, there are current trials looking not at how to augment the patient's own immune system, but how can we give exogenous immune cells to impact the responses to chemoimmunotherapy. While some current trials are looking at NK cell infusions for this purpose, my lab and our group focuses on gamma delta T cells. So gamma delta T cells are actually rapidly gaining traction as a novel potent cellular therapeutic, and we'll talk about some of the reasons why. They're really unique in that they straddle the divide between the innate and the adaptive immune systems. They actually do not express the CD4 and CD8 co-receptors that you see on alpha beta or your typical CD4, CD8 positive T cells. And as such, they are not restricted to major histocompatibility molecules such as MHC complexes. This really provides a great opportunity for an off-the-shelf therapy from a healthy donor, as gamma delta T cells should not cause GVHD. In terms of their innate immune properties that make them really intriguing as an anti-tumor immune cell, the increased metabolism of tumor cells actually stimulates the overproduction of a secretion of phosphoantigens in the tumor cell. That in turn causes a conformational change in these receptors called butyrophilins that are directly sensed by the human V gamma 9 V delta 2 T cell receptor. In addition, like NK cells, gamma delta T cells also express receptors that recognize stress antigens on the cell surface of our tumor cells. So both of these properties lead to the activation of the T cell through these receptors that ultimately leads to a death receptor or perforin and granzyme mediated killing of the tumor cell without any engineering. So, how do they play a part in the adaptive immune system? Well, they actually secrete cytokines that recruit in other cells of the adaptive immune system, and they can even actually prime other cells and stimulate them to express more MHC antigen products to recruit in more immune cells to have a robust anti-tumor response. But importantly, for these purposes and for combining with chemoimmunotherapy, they express very high levels of the Fc gamma receptor 3 or the CD16 that recognizes the antibody coating the GD2 on the tumor cell. So interestingly enough, others have gone on to show that pooling tumor-infiltrating immune cells across adult cancers, and specifically in solid tumors, which is that bar on the right, showed that high levels of T cell fractions correlate with superior survival in patients, and that actually intratumoral gamma delta T cells had the most significant favorable prognostic signature, even above your typical TILs or tumor-infiltrating lymphocytes, such as your CD4 and CD8 T cells. And so my collaborator, Dr. Trent Spencer here at Emory, standardized a protocol to reliably expand gamma delta T cells ex vivo from donor-derived peripheral blood mononuclear cells. And we do this by giving IL-2 and zoledronate to enrich for activated gamma delta T cells. What's really important is that Trent created this expansion protocol in serum-free media and was able to successfully expand them to clinical grade numbers to really support their translation. Zoledronate is used to expand these cells because it blocks a key enzyme in the mevalonate pathway, which is called FPP, and leads to accumulation of isopentyl or a phosphoantigen called IPP, which in turn promotes gamma delta T cell expansion and activation. And what we saw here was that the starting numbers of gamma delta T cells really predicted the ending number. And importantly, they had an anti-tumor response against neuroblastoma cells in vitro. Jackie Zoin, who was in Trent Spencer's lab, a graduate student at that time, demonstrated that neuroblastoma, not only patient apheresis products could be expanded, but they expressed very high CD16. In addition, healthy donor samples could be expanded equally, and they also expressed high CD16. This translated over to in vitro studies showing that when you give dinutuximab in combination with expanded gamma delta T cells, we had a much more impressive anti-tumor cell death. So we're really excited to bring this into the mouse model, but first I'll show you a little movie that I always find is kind of fun. The green are the neuroblastoma cells. Dinutuximab was pre-treated of these cells before the blue gamma delta T cells were added. These are unengineered cells. And as you can see, over a 4-hour period, the gamma delta T cells can keep bombarding these immune neuroblastoma cells. And even you can see them engulfing some of the tumor cells that likely lead to their presenting them to other immune cells later on if they were present. And so as you can see, they really pop open by apoptosis in response to these really active little guys, which are our gamma delta T cells. So again, that really excited us to bring this into an in vivo model, but unfortunately, we did not see the robust responses we saw in vitro. We confirmed that the anti-GD2 antibody bound to our neuroblastoma cell line-derived xenografts in our NSG mouse to the same extent that they did in vitro. So we wondered if this was due to poor gamma delta T cell trafficking and or activation. So we wanted to figure out a way to make these tumors more noticeable to our gamma delta T cells in the mouse. And temozolomide, which is used in the relapsed refractory cassette of chemoimmunotherapy with dinutuximab, is an alkylating agent that actually methylates DNA on guanine residues and can cause increased stress antigen production on our tumor cells. And as I mentioned, gamma delta T cells actually express the receptor NKG2D that recognizes these stress antigens or these NKG2D ligands that these chemotherapy agents can upregulate. And when we added temozolomide to this chemoimmunotherapy cassette, we really saw a robust anti-tumor response, as you can see here in this waterfall plot. And the in vivo data looking at tumors that we took out of the mice, we see an increase in the stress antigens on the tumors treated with temozolomide versus just dinutuximab alone with our gamma delta T cells. And so this led us to think about how we could translate this chemoimmunotherapy and gamma delta T cells into our patients. So the first thought is really going with what most people do when you're bringing a novel cell therapy in, use the patient's own cells. So I failed to mention that gamma delta T cells only make up about 1 to 3% of the peripheral blood mononuclear cells. And the good thing is our patients actually have to undergo pheresis to get stem cells in anticipation of future stem cell transplants that they get as standard of care. And as being such a small subset, pheresis would need to happen for our patients or whatever donor we use to get enough gamma delta T cells to expand to clinical grade numbers for a therapy. Unfortunately, the demand for high-risk neuroblastoma apheresis products has become very high at diagnosis. And repeating apheresis at relapse can be difficult to mobilize sufficient cells for storage. For example, as I mentioned, you have 2 autologous stem cell transplants, which uses 2 bags of your apheresis products. In addition, MIBG therapy, which requires stem cell rescue, has also been added to induction, and that trial was recently closed. So if that shows positive results, that may become added to our standard of care on top of 2 autologous stem cell transplants. And what I want to really focus in on is that T cells from newly diagnosed patients may not be the best source for our therapy. Dr. Das, who was previously in David Barrett's lab at the Children's Hospital of Philadelphia, showed that T cells from newly diagnosed high-risk neuroblastoma patients, following just 1 cycle of induction chemotherapy, have exhausted T cells that fail to expand in vivo. Now, those were alpha beta T cells that he tested. However, we can anticipate that most of our immune cells are going to be pretty exhausted after a cycle of chemo. So this made us postulate whether healthy donor cells were a better source and could possibly provide more, as well as maybe more potent in vivo in our patients. And this led us to propose the trial, which is a phase 1 study of ex vivo expanded gamma delta T cells in combination with dinutuximab, temozolomide, irinotecan, and zoledronate in children with relapsed and refractory neuroblastoma. And we added zoledronate because it's used, as you see, to activate gamma delta T cells. It also has anti-tumor properties preclinically for us in the lab. And most importantly, it already has pediatric dosing in neuroblastoma patients by prior trials, showing that it was very well tolerated. So typical primary objectives for our phase 1 trial were to determine the recommended phase 2 dose of the cell therapy dose of allogeneic expanded gamma delta T cells on fixed dosing of dinutuximab, temozolomide, irinotecan, and zoledronate, and to define the safety, toxicity, and preliminary efficacy of this regimen. Importantly, we have exploratory objectives to determine if our T cells stick around in our patients. So we do serial blood draws after our patients receive their cells. And we're performing next generation chimerism sequencing of this of our gamma delta T cells in collaboration with Dr. Melody Zhang at Stanford. We also are doing serial immunophenotyping to determine the effects on the patient's immune system by these activated gamma delta T cells. And here's just a schema of our expansion protocol. Importantly, we actually deplete the product of alpha beta T cells on day 6 because these are our little guys that are going to cause graft versus host disease, and they can be expanded a little bit in our product. After 12 days of expansion and that depletion on day 6, we get less than 0.4% of alpha beta T cells in the product, which leads to less than 0.02% of our naive CD27 and CD45 RA positive cells, which are the ones that cause GVHD. And this is well below the limit for a stem cell transplant that requires allogeneic immune cells from another patient. Little study details, we give our typical 5 days of irinotecan temozolomide with dinutuximab starting on days 2 through 4. Again, as I mentioned, those are at fixed dosing. And then on day 6, 24 hours after the completion of irinotecan, we give our zoledronate followed by our gamma delta T cells. And that's just to ensure that our T cells aren't affected by the chemotherapy. Because dinutuximab effects stick around for a long time, as many of you guys may know, we give another dose of gamma delta T cells on day 13 to capitalize on that, knowing that our T cells may be more short-lived than typical alpha beta T cell. This is a 3+3 design. These are for frozen, then thawed cells that are given intravenously. We have 3 cell therapy dose levels, as you can see here below. And we get we use a different donor per course if it's available. And we're also checking HLA antibody evolution over the course of receiving different donor therapies. But we are not choosing the therapies based on the HLA phenotype. So updates on the study, we have completed dose level 1 with no DLTs. Dose level 2, we've had 2 out of 3 complete treatment with no dose limiting toxicities. So now we just need to finish that 1 dose level to get to dose level 3. We are happy to say that allogeneic gamma delta T cells are safe and tolerable and feasible to give as an outpatient. Our second dose is given in our BMT clinic, and we've had no issues with that. I can't speak to responses right now, but just taking into account that these are lower doses and we haven't gotten to dose level 3 just yet. Our study has been amended to include relapsed metastatic osteosarcoma to improve accrual, given that a lot of patients have seen chemoimmunotherapy up front and want other options, because osteosarcoma is a GD2 positive tumor. And we've treated 2 osteo patients so far that tolerated treatment at dose level 2. And I'm also pleased to announce that we've received funding to support the opening of our trial to a multi-site level to complete our expansion phase at the recommended phase 2 dose. And we thank the Isabella Santos Foundation for that. And so now I want to take a little bit of a detour to talk about what we need to do to make better gamma delta T cell therapies after we complete this phase 1 trial. And one way to do that is possibly to pick other antigens to target. And why is that important? Well, as you can see here, GD2 has really been almost exhausted in terms of its application in relapse refractory neuroblastoma. And as you can see here with these trials, just specifically Children's Oncology Group trials, but there are others that are giving anti-GD2 antibodies to newly diagnosed high-risk patients, which may cause changes in the GD2 expression to allow them to respond if you give it again at relapse or progression. And so this really begs the question, is GD2 what we want to be using in the relapse refractory setting? And as I mentioned right here, in the relapse refractory, these are just trials that are antibody GD2 therapies. I'm not talking about the CAR T cells that are focused on GD2, which so far there have been some that have shown some responses in previously dinutuximab treated patients. However, targeting GD2 can also be wrought with many toxicities due to its expression on normal tissues, like pain fibers and the CNS. Other research suggests that within a single tumor, GD2 could be heterogeneous, and it may be downregulated from the tumor cell surface following chemotherapy and progressive disease, as you can see here from bone marrows that have been enriched on Children's Oncology Group biology trial done by Dr. Pat Reynolds shows that the MFI of GD2 goes way down in our progressive disease samples. And so this really brings about the question of whether the cell there surfaceome changes in response to chemotherapy, and how does that affect our choice of antigen to target, and when we give novel immunotherapy approaches, and can we find different targets beyond GD2 to offer to these patients? So, to investigate this question, we collaborated with Dr. Ronghu Wu in the School of Chemistry at Georgia Tech to use his high throughput cell surface capturing technology to unbiasedly evaluate changes in the cell surfaceome before and after chemotherapy in a mouse model of neuroblastoma that's treated with a typical induction cycle of neuroblastoma therapy. What we did was we treated established xenografts that were pretty well established and actually ended up growing through this chemotherapy treatment, so very aggressive models. And then we labeled the N-glycoproteins and then digested them and enriched for those cell surface labeled N-glycoproteins, and then performed mass spec to evaluate what proteins that were specifically on the cell surface of our chemotherapy treated models. This led to the identification of about 203 unique cell surface proteins. And I'm not going to go into too many details, but through a algorithm that we had created to look at normal cell expression of our targets, to look at the cell surface conformation of where the proteins localize, as well as to see patient survival effects, tumor dependency effects, and other literature that supports this as a potential immunotherapy target. We actually identified protein tyrosine kinase 7 to be highly expressed in neuroblastoma with minimal expression in normal tissues by these data sets. So what is PTK7? It's an inactive tyrosine kinase that interacts in the Wnt signaling pathway. It's involved in cell adhesion, migration, cell polarity, proliferation, and invasion. So you can imagine it's a perfect candidate for a cancer-associated gene. It is highly expressed in adult cancers such as colon, cervical, breast, and lung cancer. And inhibition can actually inhibit tumor-initiating cells. So we thought this was a really good candidate to go after and validate in our neuroblastoma models. Here we show by flow cytometry that PTK7 is very highly expressed on the cell surface of both our cell lines as well as our patient-derived xenografts. And these efforts were led by Hunter Jonas, who is a former postdoc and now assistant professor at the Children's Healthcare of Atlanta. And what we show is that in primary tumor samples, that PTK7 is highly expressed on the cell surface of fresh tumor that came from patient biopsies, and that post-induction patient biopsies had even higher expression of PTK7 on the cell surface after 5 cycles of induction chemotherapy. We've actually created patient-derived xenografts from these primary tumors and shown very equal expression of PTK7 before and after treatment that we can use for our preclinical testing. Importantly, those data sets that we monitored for our algorithm were really looking at adult uh, normal organ tissues. And so what we did was we created a pediatric normal organ microarray in patients ages 1 to 5 to really understand in the developing patient, pediatric patient, whether their normal tissues expressed our target of interest being PTK7. We're very pleased to show that even more so than the adults, that pediatric normal tissues have low to no expression of PTK7, whereas it's more moderately expressed in adult normal tissues. And interestingly enough, we looked beyond neuroblastoma and found that it is highly expressed in other pediatric tumor types, such as rhabdomyosarcoma, which we confirmed with some cell lines and PDXs by IHC, osteosarcoma, as well as Wilms tumor is up there, and other pediatric tumor types. So this really does extend in pediatric cancer beyond just neuroblastoma. To really talk about how we can make better preclinical model systems for immunotherapy testing. As I mentioned, we usually use human-derived tumor cell lines, or if we're lucky, PDXs. These are injected into immunocompromised mice, which have an unrealistic TME because they have little to no immune cells in the tumor or in the mouse itself. Immunocompetent mouse models are better, but humanized mouse models are expensive and ultimately develop GVHD, leading a very narrow therapeutic window for treatment. They're slow to accrue with our transgenic mouse models, where you depend on homozygous pups to have that penetrance of the tumors evolving. And most importantly, for our purposes, there's no murine homolog to the human gamma delta T cell. There are murine gamma delta T cells, but they do not have the same butyrophilin recognizing gamma delta TCR. And concomitantly, our neuroblastoma-derived Muri neuroblastoma tumors actually do not express butyrophilins. And so because of that, we really cannot use a mouse model of neuroblastoma that is immunocompetent, whether it's a syngeneic or transgenic mouse model for gamma delta T cell testing. So this leads to our need for a more accurate high throughput model. And so Hunter Jonas, who I mentioned was a postdoc, is now on faculty at Children's Healthcare Atlanta, as along with a graduate student, Emily Bonilla, in my lab, and Katrina Johns, an undergraduate student at Georgia Tech, have now been working to create organoids through a matrigel mediated system to create a multicellular organoid to be able to answer these questions in a high throughput fashion. And what we can do is we can actually select for the immune cells we want to use, they're being anti-tumor or pro-tumorigenic, and co-incubate them with neuroblastoma cells to really characterize how they interact and how they impact each other's function, as well as how they impact therapy response. So what we did was we took CD3 enriched T cells, combined them with neuroblastoma cells, and incubated those together for 5 days. We recapitulated that co-culture experiment we showed that was just done in a typical 96-well plate fashion, but did it with organoids this time, and added the purified PTK7 targeting TCE to the media that covers the organoids, waited for 1 day, and then extracted the immune cells and the neuroblastoma cells and performed flow cytometry. Here is evidence of the breakdown of the CD3 positive T cells compared to the neuroblastoma cells in the organoid. So we didn't have complete abrogation of the immune cells in the organoid, and we've actually been able to show that the immune cells stay alive for up to 2+ weeks in our organoid model, which is really great for immunotherapy testing. And what was really cool is it's exactly what we would expect, that the CD4 and CD8 T cells did not have any activation in response to our neuroblastoma organoid model when just co-cultured alone. But when you add the PTK7, this actually should be a TCE, T cell engager, we saw a really impressive activation of both our CD4 population as well as our CD8 population. And as we would expect, this gamma delta T cell population, which makes up a small subset of our peripheral blood mononuclear cells, and here are CD3 positive enriched cells. These are not expanded, these are not activated cells, but they are activated in response to co-culture with neuroblastoma via their direct recognition of those neuroblastoma cells through those different receptors that we talked about earlier. So that was really exciting to see that it recapitulates exactly what we would expect. And then when you add in your PTK7 targeting star with your gamma delta T cells, you see a really robust activation of our non-modified, non-expanded gamma delta T cells in this CD3 enriched portion of immune cells. So this really shows that these TCEs can engage peripheral blood patient immune cells, but also that these organoid models can be used for really multicellular cultures and immunotherapy testing. But the one thing that this doesn't take into account are different aspects of the TME that are underappreciated to impact therapy response. And that would be vasculature, being our endothelial cells, vascular flow, and our extracellular matrix. So I've partnered with Dr. Vahid Sarpushin to create a highly tunable 3D bioprinted model of neuroblastoma and the tumor microenvironment, using a gelatin macrofill that can actually act as a bioink, and you can modify the components to reflect the ECM with collagen, fibronectin that you see in neuroblastoma. We can make this into a model that has vascular channels that we endothelialize with human umbilical vein endothelial cells, and we can actually rock these models or hook them up to bioreactors to create perfusion to mimic vascular flow. And this allows us to answer some exciting questions of how does ECM stiffness, endothelium, the cellular interactions with the endothelial cells and tumor cells affect neuroblastoma cell state. And what we found was that the dynamic rocking procedure that mimics blood flow or bioreactor blood flow can actually cause a more aggressive model of neuroblastoma as they start to migrate and invade in on each other. And we see that also with the metabolomic profile that we did, which I'm not showing here, as well as with immunohistochemistry. And so we really want to make sure that these underappreciated aspects of the TME that may impact therapy response are taken into consideration. And we really are excited to say we got a DoD grant to now combine efforts of our matrigel containing immune competent organoids in combination with our 3D bioprinted tumor microenvironment to create an immunocompetent 3D bioprinted model. This will allow us to hook these up to a bioreactor, which we have already done. As you can see here in the actual models, here's a depiction of what they look like. And then we can introduce and take away our model's cellular components to really tweeze out the culprit for therapy resistance in order to design better therapies that target that mechanism. And I hope maybe next time, if I ever present, I can share some of the data that's coming out of this collaboration. So sorry, I think I'm a little over time, so I'll be very brief. I hope I've been able to show you that GD2 chemoimmunotherapy can be improved with different radiotherapy and targeted therapies that enhance innate immune cells, and that gamma delta T cells alone can be a nice off-the-shelf partner for GD2 antibody immunotherapy and an ideal platform for engineering because they're very amenable to transduction and electroporation for engineering to improve fitness, trafficking, and efficacy. The PTK7 is an exciting new therapeutic target that we are actually working for cell therapies to target GD2 downregulated tumors and to activate endogenous immune cells through our TCE engagers, and to use and create more immunocompetent models that we hope to expand beyond neuroblastoma for these immunotherapy investigations in a high throughput fashion. And we hope to enhance our expanded cells via novel methods to improve their fitness through cytokine and engineering, their ability to be more cloaked and not recognizable so that they stick around a little bit longer. And then we're also working with Day One to compare how does a PTK7 ADC, such as Day 301, work against a PTK7 positive model, and how can we use that as an immunotherapy in neuroblastoma as well. So I'm open to questions, and I want to thank you and thank all of our organizers for the opportunity to speak, all of the amazing village that it takes to run these trials and these preclinical tests. And of course, my lab, I couldn't do it without them and without their amazing figures and all of our funding sources. So thank you so much.
Okay, thank you, Dr. Goldsmith. And as we mentioned in the beginning, feel free to post questions in the chat or Q&A function for Dr. Goldsmith as well. So our first question is involving the PTK7
Mhm.
aspect. So are there any known inhibitors or drugs that can actually modulate PTK7 function that can be used as a combination therapy with your TCE?
In terms of modulating function, because it's an inactive tyrosine kinase, you can't use a small molecule inhibitor. Um, Obviously, if you're going to use it in combination with the TCE, you don't want a degrader or something that's going to get rid of it because you want it to be recognized on the cell surface. I think, sometimes I know there have been some efforts to combine antibody therapy with CAR T therapy or ADCs, and we can try that with our PTK7 targeting ADC. I see this as an opportunity to target our heterogeneous neuroblastoma models, not just by dual targeting PTK7, but by targeting multiple antigens on the cell surface or dual aspects, so that if one gets downregulated, you still have the opportunity to target the other. So I see that as possibly um, a better path forward than things that can modulate PTK7. I don't know, however, like we see with GD2 upregulating on the cell surface, if epigenetic modifiers could enhance that cell surface expression. And that's actually something that we're looking at as we investigate how these HDAC inhibitors can enhance PTK7 targeting gamma delta T cells via modulating the immune microenvironment. But it would be super cool if it upregulated PTK7 as well.
Right, thank you. So our next question is, have you observed populations within the tumor that have become more proliferative to gamma delta exposure or the opposite?
More proliferative to gamma delta exposure, like the tumor cells become? I'm not sure what that question is asking. Could you read that again, Justin? Maybe
Yeah. So have you observed populations within the tumor that become more proliferative to gamma delta exposure?
So I wonder if they're talking about a secondary proliferation of the T cells when they meet their target. I'm going to answer that as to what I think the question's asking. We are actually creating these models to investigate this better. We haven't answered that question, but that's one of the reasons we're making these models to be able to answer this, not just with multiple models that you can take and individually look by flow, but also to do real cell and live cell imaging to monitor that response in real time. So I don't know the answer to that yet. Can gamma delta T cells undergo a secondary proliferation? Yes, they can, which is why we think they might be more ideal to NK cells, but we still need to answer that question.
And so they actually followed up and said the
Okay.
neuroblastoma cells. Have
Oh,
you observed
neuroblastoma cells.
enhanced proliferation of the actual neuroblastoma cells after
Oh.
treatment?
So we haven't seen them become, we have seen neuroblastoma tumor cells outgrow the gamma delta T cell therapy. So they grow back, which you see a lot with different types of immune cell therapies or any kind of cell therapy. We don't think this is in direct response to PTK7 targeting. We think it's because our gamma delta T cells aren't sticking around long enough. And having that effect. We have been able to show serial killing of neuroblastoma when we add in different cytokines. And as such, we're adding that into our therapy at the preclinical stage just right now. But we don't think that by targeting PTK7, we're causing a secondary proliferation because it's a tumor targeting effect, a tumor proliferation effect. When we inhibit PTK7 in our neuroblastoma by CRISPR-Cas9, we see no changes in proliferation or chemotherapy response. So while there's not necessarily what we call a dependency, we still think it's a good immunotherapy target based on the low normal tissue expression. I hope that answered your questions.
Yes.
Okay.
So the next question is, what factors have you explored to influence gamma delta T cell trafficking to the tumor? And is that an issue after they're infused?
Definitely an issue, as we see with a lot of different immune cell therapies. Actually making them hone to the target via recognizing different cell surface antigens has improved their trafficking, which is why we're, tagging them with PTK7. We've talked about adding in chemokines to do this as well. Actually, our gamma delta T cells express a host of chemokines after expansion, like CCR2, so we hope that that helps them. They naturally migrate to via solid tumor gradients of chemokine, so that makes them a positive property. But we're also looking at other methods to kind of bring them to the tumor that I can't really talk about just yet. But yeah, we're working on that as we speak.
Okay. And our next question is just, I think, a more broad question, which is when you do the surfaceome analysis, you
Mhm.
identified a number of different receptors that could be potential targets for neuroblastoma. How many of those do you think would be applicable to other types of tumors, and how many do you think would be more specific to neuroblastoma when you do these types of analyses?
Oh gosh, I mean, because it's unbiased, that is a great question. Off the top of my head, I don't know how many would be like applicable to multiple tumor types. But I would say ideally you'd want to find one that's applicable to multiple tumor types, and that is one aspect of the diagram that we were looking at. What's the expression in other tumor types, which is the literature search that we did, not just in pediatric tumors, but adult tumors, because we know immunotherapies are often, like the drug type therapies are often initiated in adults first. But I think given that we're modeling it in a neuroblastoma tumor and it's a neural crest-derived cell, you might expect to see some of these antigens like we do, like NCAM1, LCAM, things that are expressed on neural crest-derived tumors, melanoma, and other things like that. You would expect to see them have kind of similar expression levels, but that is one of the things we look at during our pipeline to see if we can have it be more applicable beyond neuroblastoma. It's a great
Our
question.
our next question is, in the initial studies, were the gamma delta T cell engineered against GD2 or any other markers?
Yes, we have engineered GD2 CAR expressing gamma delta T cells, as I showed earlier, a GD2 TCE secreting gamma delta T cell. We just happen to be doing kind of these things in parallel, and we discovered PTK7, and we loved the idea of a new target. We have not engineered them to target other neuroblastoma specific antigens such as GPC2, B7H3, or others. I have a graduate student in my lab who has identified some cell surface targets for CNS relapse of neuroblastoma, and he's engineered gamma delta T cells to recognize those via CARs. So we hope to share that in the near future with the publication. So, but we just went with the PTK7, not for the novelty, but to really give our patients who are not responding to GD2 therapies, which we think will be more in the future, an opportunity and an option for therapeutic immunotherapy and cell therapies.
Our next question is, do gamma delta T cells undergo similar exhaustion process as alpha beta tumor infiltrated T cells, and do checkpoint molecules matter?
It's a great question. Yes, they do. And one thing that we have noticed is that giving zoledronate with it helps prevent that. And we know certain cytokines like IL-15 can help prevent that exhaustion as well, which is when I mentioned that serial killing, when we give IL-15, either create our cells to secrete IL-15 or give the superagonist D803 or N803, that we are able to see that serial killing, and the ability to serial kill prevents is showing you that they're not exhausted, but we also phenotype them to show there are certain checkpoints that are upregulated just with activation and expansion of our gamma delta T cells, such as TIM3, but there's a lot of literature suggesting that that may not be an exhausted phenotype in our gamma delta T cells as you see with alpha beta T cells. But we are trying to engineer our cells to be more fit by overcoming that exhaustion. And we also do see some tonic activation. And so we, like the alpha beta T cell community, are trying to overcome that with novel engineering approaches.